This video is part of an online course of multivariable calculus, and I'm going to talk about how to compute double integrals in polar coordinates. Why do we do that? It's just because some functions are simpler in polar, or even the region of integration is simpler in polar. So let me start. The goal is this. We want to compute double integral of a function of two variables x and y, dx dy, over the region R using polar coordinates. Okay, so why do we do that? It's just because polar coordinates or basically I want to say that the polar transformation is useful if the function f or even the region R have simpler explanation in polar. So for example, the region R is a circle, it's a disk, that's like that. Or it's like part of a disk, or even it's like part of a donut. It would be something like this. Or even the function f has x squared plus y squared, or something that you can basically transform it more easily into polar. So to compute this double integral in polar, we're gonna transform r in polar. We're gonna transform x and y in polar. So how do I do that? I'm gonna say x is r cosine theta, and then y is r sine theta, and so everything would be in polar. Now the question is this: what can I do for dx dy? How can I transform this into polar? So the question is this: in Cartesian coordinate, dA, the element of area, is dx times dy. What is dA in polar coordinates? Before I answer this question, I would like to go over polar rectangles. What is a polar rectangle? Polar rectangle has some equation like this. R is some r and theta, okay, some points r and theta, where r is between a and b, and theta is between alpha and beta. Okay, so let me graph it. I'm gonna use this one. Okay, this is x-axis, this is y-axis. So I'm gonna have a ray for theta equals to alpha, and I'm gonna have another ray for theta equals to beta. So this is theta equals to alpha. So this angle in here would be alpha. I'm gonna have another ray for beta, and this ray is theta equals to beta, and then r is between some a and b. So a piece of a circle where r equals to a, for example, is here. So this is r equals to a, and then part of a circle of radius r equals to b is like that. So the polar rectangle would be something like this. Okay, so all the points r and theta, where the first coordinate r is between a and b and the second coordinate theta is between alpha and beta. Okay, so we call this, as you see, it is not the actual rectangle, but it's a rectangle in polar. We call it polar rectangle. So now let's go back to the area element, dA. How can I transform dA into polar? What is dA into polar? So I'm gonna say that we're gonna partition the polar rectangle R into smaller polar rectangles. Polar rectangles. Basically angular sectors. Angular sectors. How? I'm gonna graph it like this. So let me have it like that. So you see, I'm gonna basically partition it into different R's and also different theta. Okay, so let me emphasize that this part in here inside the red area would be my polar rectangle, and I partition it into angular sectors, okay, as before. Now let me just pay attention to just one small piece. Do you remember in the Cartesian case, when we wanted to find the double integral, we partitioned the region R into smaller rectangles. In each of the rectangles, we pick a sample point, and then we consider the value of the function at that sample point, which gives us the height of the volume of the solid that we wanted to calculate, right? So I'm gonna do the same thing in here. Let me graph what we have in the small rectangle. I'm gonna zoom in and say that this is, for example, R equals to, for example, this is actually theta. I'm gonna have like this part would be delta theta, right? And then I'm gonna say that, for example, up to here it's R, and then I have like a delta R in here. So I basically just zoom in into one of the angular sectors, and then I'm considering, oops, this one as my delta A, just one of the angular sectors I zoomed in here. So look at delta A. Okay, delta A is something like this. Okay, a polar rectangle, one side is what? One side here is actually delta R, and then the other side in here, it would be R delta theta. Using geometry, if you remember, the length of this arc in here would be R times delta theta. So this is R delta theta. Okay, so delta A is approximately delta R times R delta theta. Okay, it would be the area of the polar rectangle. This is smaller polar rectangle, okay? And then so I have the area of the small pieces of them, and then I'm gonna pick just one sample point in the middle, okay? And then I say that f of the sample point that I choose, yj for example, this, f of that would give me the height times the area of the base, would be approximately this, delta R delta theta, okay? and then I'm gonna add them up for all I and j's. Okay, so I have basically two sums. I can write it as just one sum or two sums, and then I'm gonna say that the double integral of f dA over the region R is approximately this sum in here, the height times the area of the base for each one of them. It gives me the volume, and this is approximately the double integral would be the limit of that, but approximately is this. So now we're gonna take the limit, and when I take the limit delta R delta A, the change the area of the smaller polar rectangle, it would be dA, and this is R delta theta. When I take the limit, it would be R d theta, very small pieces. So if I want to define that, it would be the double integral of f of x y dA over the region R. It is the double integral. In polar, it would be what? Instead of every x, I'm gonna write R cosine theta. Instead of every y, I'm gonna write R sine theta. Instead of the area element of the area, I'm gonna write R d theta. Okay, based on that definition that we have in here, and then we're gonna change R into polar. Okay, so that's how we compute a double integral into polar coordinates. Okay, and the next video I'm gonna solve some examples, and then you will see how we can calculate that.